So welcome to the third video on reaction rates. I hope the first two have been helpful. Do go back to them, revisit them, and what we're now going to do is see how we can use the practical work that has been described in the previous videos, how we can use that to measure the rate of reaction. As we've already seen in the previous videos, then the rate of reaction is defined as the changing concentration or mass or volume of a reactant or a product to a substance in the unit time. And so the units would be grams per second, cubic centimeters of a gas per second, or moles per litre per second. In a rates investigation, we set up our experiment and we collect a set of results for a period of time. We then plot a graph, we draw a tangent at the beginning of the graph, and we calculate the gradient of that tangent. And as we can see on this graph here, the initial rate of reaction is the gradient of the tangent at the beginning. So we collect a whole set of results, but we're only interested in that initial rate. Once we have one set of results, we stop the experiment, we clean the apparatus out, we set the whole experiment up again, but this time we change one variable. So for example, we may change the concentration of an acid, we may change the surface area of a solid, and we run the whole experiment again, collecting an entire new set of results. Having collected the results, we plot a graph, we draw a tangent, we calculate the gradient of the tangent, and once again we now have the initial rate. So now we would have two experiment sets of results, and we then repeat this. So ideally we probably want 5 sets of results, so for either 5 concentrations and 5 initial rates of reaction. The information at the bottom of this page refers to the disappearing cross experiment, the reaction between sodium thiosulfate and hydrochloric acid, and referred to this on the first video, where we assume that the mass of solid produced each time to obscure the cross would be the same. And therefore when we calculate rate equals mass of solid divided by time. Because the mass of solid is a constant, we can then say that the rate is proportional to 1 over time. It doesn't equal 1 over time, but it's proportional to 1 over time. So when we record any set of results, we are interested in 2 factors. One is the initial rate, as this graph shows here, the initial rate of reaction, and 2, the endpoint. So we want to know the initial rate and the endpoint. And we are going to look at both of those in the graphs on the following pages. So although there are 4 curves on this set of axes, we only need to talk about any 2 at a time. So let's start with our first set of results. So our first set of results is labelled as A. And that's the one I'm just drawing over at the moment. So we then change one of the variables. And what it's suggesting here on the left hand side is that we have a different volume of the same initial concentration. So this would be a smaller volume. And if we halve the volume and then consider what would happen to the shape of curve B if we halve the volume but keep the concentration the same. Because the concentration is the same, the volume of gas will be produced at the same rate, and therefore our initial rate will be the same. Curve B will have the same initial rate as curve A. Same volume of gas will be produced in the same time. However, because our volume of acid is half, then the total volume of gas will be half. And so when curve B levels off, the final volume of gas will be half of the value of curve A. If we now compare curves B and C, C may be at a lower temperature than B, and so the rate of reaction with curve C is slower, and therefore we have initial rate of reaction, the gradient is lower, but because all the other conditions are the same, we'll end up with the same volume of gas produced, so the endpoint for C would be the same. And finally, if we compare B with D, D may have a solid where the surface area is less. Again, the rate of reaction will be lower. The initial rate of reaction would have a lower gradient. But because all the other conditions are the same, then the end point, which is the total volume of gas collected, will be the same, and so curve D will end up at the same value as C or B. So as we move on to this new slide, I want you to pause the video and I want you to think about the two factors that are highlighted in red here. I want you to think about the initial rate of reaction, and I want you to think about the end point. And then when we change a variable in our new experiment, you must consider how the initial rate of reaction is different, if at all, and how the end point will be if it is different in any way. So pause the video and think about those points. If you're now ready to move on, we're going to look at some specific examples as shown in the table here. So just pause the video and have a look at all the data in that table. So let's just focus on the experiment. We are reacting calcium carbonate with acid, and as we saw in our first video, there are a number of variables that we could change. We could change the surface area of the calcium carbonate. We could change the mass of the calcium carbonate. We could change the volume of the hydrochloric acid. We could change the concentration of the hydrochloric acid, or we could change the temperature of the hydrochloric acid. And the table here looks at changing most of those variables. Not the mass of calcium carbonate, that's being kept constant throughout, but we could change the first column shows you how the surface area of the calcium carbonate could be changed. The second column, the square brackets around HCl is a scientific notation of representing concentration. And we can change the volume of hydrochloric acid, and we can change the temperature. That just shows degrees centigrade. But we can only change one thing at a time. So we start with experiment 1. And on the next slide, we're going to see a repeat of the table. And the first curve has arbitrarily been drawn for you using small pieces of calcium carbonate with the concentration of hydrochloric acid at 2 moles per litre. We have 100 cubic centimetres of the hydrochloric acid at 20 degrees. So you now need to consider what curve 2 would look like. So I'm going to get you to pause the video, and I want you to think about the initial rate of reaction, and I want you to think about the end point. And effectively you need to sketch where curve 2 will be. Then you can repeat that task for curve 3 compared to curve 1, and then for curve 4 compared to curve 1. You can only do 2 curves at a time, and we'll end up then with 4 curves on the same set of axes. So pause the video, sketch out your work, and then when you're ready to move on, you'll see the answers. So the answers are shown on the following slide. So just pause the video and have a look at your 4 curves, think about them, and then I'll talk you through them. So curve 2, comparing curve 2 to curve 1, hope you appreciate that the fact we have larger pieces of calcium carbonate means that the initial rate of reaction will be slower, but because all the other factors are constant, we'll end up with the same volume of gas produced and therefore the same endpoint. With curve 3, we still have the same concentration of hydrochloric acid. The fact that we have less hydrochloric acid is not going to affect the contact between the hydrochloric acid and the calcium carbonate in the first few seconds of the reaction, so the initial rate is going to be the same because the concentration is the same. However, we have large particles, so curve 3 and curve 2, because they have large particles, will have slower rates of reaction compared to curve 1. But with curve 3, because our volume of hydrochloric acid has been halved, that will lead to half the final volume of carbon dioxide being collected, and so our endpoint is half. If we compare curve 4 with curve 1, then we see that the size of the calcium carbonate is the same, the temperatures are the same. Although we have different volumes of hydrochloric acid, that's not really going to make any difference to the rate of the reaction, because the initial reaction is going to be determined by the contact between the calcium carbonate and the volume of hydrochloric acid. So having 50 or 100 isn't going to make a lot of difference, but you'll notice the concentration of hydrochloric acid is double in 4, at 4 moles per litre, and so therefore the initial rate would be faster, but the number of moles of hydrochloric acid is the same. 50 cubic centimetres of 4 moles per litre is the same number of moles as 100 cubic centimetres of 2. So therefore that's going to lead to the same volume of carbon dioxide being produced. So curve 4 has a steeper initial rate of reaction, but the endpoint is the same as curve 1. So if you're happy with the shape of those three curves compared to curve 1, then we're going to move on to the next slide, where we see that there are 3 more rows been added, 5, 6 and 7. So pause the video, think about what the shape of the curve will be, the initial gradient and the final endpoint for those 5. We're still going to compare these 3 extra curves to the 4 you've already drawn, particularly curve 1. And so you should now have 7 curves on the same set of axes. So pause the video and complete the task of drawing curves for 5, 6 and 7. So the data is not repeated on the next slide, so perhaps if we just focus on curves 3 and 5. In 3 and 5 they're both large pieces of calcium carbonate. It's the same temperature. The key difference is the fact in 5 the concentration is half compared to 3. So curve 5 would have a slower rate of reaction, therefore the initial rate of reaction would have a lower gradient, but have the same endpoint as 3. And that's shown on the next 6 and 7. If we compare curve 6 and curve 1, calcium carbonate is the same surface area, the concentration of hydrochloric acid is the same. We have double the volume of hydrochloric acid, therefore the volume of carbon dioxide collected will be double. But the key difference is the fact that curve 6 is at a higher temperature compared to curve 1, so therefore the rate of reaction is going to be faster. And if we now consider curve 7 with curve 6, we'll notice that the calcium carbonate is in powder form compared to small pieces, so that means curve 7 will have a faster rate of reaction than curve 6. All the other factors are the same, temperature and concentration, so therefore curve 7 would have the fastest rate of reaction but the same endpoint as curve 6, and that is shown on the slide. So there's 5 at the bottom with a slower rate of reaction compared to curve 3 but the same endpoint. Now for curve, we skip forward, so we'll look something like this. Next slide. So I hope you've got all those correct. So at this point you might need to flick back to the table on the previous slides and these graphs to make sure you're fully confident with distinguishing between the initial rate of reaction and the final volume of carbon dioxide in each case. If you're confident with those issues, then we can move on to the next slide, which just refreshes the effect of increasing temperature on the rate of reaction. So we start with the blue curve, which is at a lower temperature, and we're then going to increase the temperature. Now when we increase the temperature, the maximum gets shifted to the right and is lower. That's the most probable energy. Remember, the area of both curves will be the same, but the number of molecules which have the activation energy or greater is greatly increased. And that explains why a slight increase in temperature can have a much more dramatic effect on the rate of reaction. So pause the video, go over the work on this slide, and then we'll move on to the next slide. In the next slide we recap the effect of increasing the surface area and the effect of catalysts. So in your own time, do review that work. And once you've reviewed this work, then that is the end of this show. So I hope you've enjoyed it.